Okay, this is the one. This is the one you needed. We're going to explain those Lotka Volterra competition model graphs that no one seems to explain very well. You're going to get it here. You're going to understand it. Hi, I'm Sue Glenn. This is my series of lectures for ecology, and today we're going to look at mathematical and lab models of competition, focusing on the Lotka Volterra competition model. And this is some of the stuff in this is based on the chapter 13.2 in the textbook Ecology Concepts and Applications, written by Manuel, Molles, and Sher, and published in its 8th edition by McGraw-Hill in 2019. All right, so let's get going. Now, just to acknowledge the fact that mathematical models are oversimplifications of nature, and we really can't understand interspecific competition without looking at lab models and field models as well. And they really are complementary to each other. So, although mathematical models might sacrifice accuracy, what they can help you is look at exploring the variables and seeing in what circumstances certain variables become important. So it allows you to focus in on what you have the most likelihood finding a pattern in. And it gives you a lot of control that you wouldn't obviously have in the natural environment. Metz reviewed research on and models, population models on Tribolium beetles, and he came up with some generalizations which I think expand much beyond the beetles. One is that models are abstractions or simplifications. They're not supposed to have everything in them that nature has. They are man-made, but even though they're partly deductive, they are based on things we know about nature, and so they are partly empirical as well. And they do provide us useful insights that we wouldn't normally have easy access to. So they give you a way of thinking about things. So we've already talked about competition within individuals, within a population of individuals of the same species, because we talked about the logistic growth model, which had intraspecific competition. As the population got bigger, that became more intense. So when we looked at the growth rate then of the population, so the change of the population size over time, it was dependent on the intrinsic growth rate of the population, so it's maximum possible growth rate, times the population size. So we had that exponential growth component, but then we added in a factor that was 1 minus n over k. So remember, n is the population size and k is the carrying capacity. And so this is showing you that the closer you get to the carrying capacity, it would slow down your population growth. You can rewrite this equation, though. We can rewrite this particular term, and we can look at it in terms of two different species. So we could start with species 1. So the population size of species 1 equals species 1's maximum growth rate. So I'll just put an M1 for species 1's growth rate times species 1 population size. And then we're just going to slightly rearrange this component of the equation, and we're going to say 1 is k over k. So we're going to have the k minus n over k. It's the same thing, and we're looking at species number 1 here. At the same time, we can do the same thing with species number 2. And this is something that you're already familiar with. So as the population of each species approaches its carrying capacity, its population growth will slow down because of intraspecific competition. So we already have an idea as to how important intraspecific competition is. Now, all we do now to make this equation into the competition equation is we're going to add an additional term into this part of it. So in that case, I'm going to take the population size of species number 1. I'm going to use blue on this second. I'm going to do species number 1 to start with. So it starts out the same. We have the carrying capacity of species number 1 minus its population size minus, and now we're going to add in competition with species number 2. And so we have something known as the competition coefficient, which is the impact of species number 2 on species number 1. So I have an alpha 1, 2. And so alpha is the impact on 1 given by species number 2. And then we have the population size of number 2. So the bigger the population of species number 2, the more negative effect it's going to have on the growth rate. And then once again, we're just going to divide that by the carrying capacity of species number 1. And we can write the same equation out for species number 2. So we have, species number 2 we're doing in red. Species number 2 equals the growth rate of species number 2. Oops, got a mistake in there. That's not the carrying capacity. That is its population size. And here's its carrying capacity minus its population, just like we had over there, minus, and now this time we're going to put the effect of species 1 on species 2, and this is going to be the population size of species 1. Up there, that was the population size of species 2. And then we're going to divide that by the carrying capacity of species 2. So in these models, the rate of population growth of a species is reduced both by individuals of the same species, conspecifics, and so the conspecifics are shown right here. And actually, we're basically saying that the impact of that conspecific, it has a implicit number 1 right here. So the size, the amount of intraspecific competition is the number 1, and then the amount of interspecific competition is going to be these competition coefficients. So these competition coefficients are the competitive effects of the competing species. So alpha 1, 2 is the effect of an individual of species 2 on an individual of species 1 relative to the competitive effect of your own species. So it's looking at those two numbers in contrast to the other. If alpha 1, 2 is equal to 1, then the amount of interspecific competition from the other species is equal to how much your own species is doing to you. If it's less than 1, it's more mild than what your own species is doing to you. And if it's greater than 1, you know it's going to be more intense than what your own species is doing to you. Here it is typed out nicer just in case you can't read my handwriting. So the Lotka Volterra equations for each different species in competition for interspecific competition and intraspecific competition are included in here. So if we look at the first equation, the change in the population of species number 1 over time is equal to its growth rate, its maximum growth rate times its population size, and then that's going to be modified by carrying capacity minus its population size. So this is intraspecific competition here, so there's like a hidden number 1 right there. And then you're also having a negative effect of species 2 on species 1. And so there we have interspecific competition, which includes the competition coefficient of alpha 1, 2, which is the individual effect of an individual of species 2 on the rate of population growth of species 1. And then we just look at the same thing. We get the same thing for species 2. And so once again, it has an implicit number 1 right here for intraspecific competition. And then so the competition coefficient for intraspecific competition for both of them is always 1. And then you've got the interspecific competition, which is the impact of species 2 on impact of species 1 on species 2. So if we look at these equations, what happens to the growth of the population as the population size increases? What does a competition coefficient of greater than 1 mean? And what does a competition coefficient of negative 1 mean? So I'm going to work through those on the next slide. I'm just going to take the equation for species number 1 and take a look at the impact of interspecific competition, the competition with species number 2. So let's just say that the impact of species number 1 on itself, intraspecific competition, is the same as the impact of the other species on it. So remember we had a number 1 here, like minus 1 times the population size is the same as minus the population size. So if the impact of species 2 on species 1 was equal to the impact of species 1 on itself, was equal to 1, so interspecific competition was equal to intraspecific competition. In that case, this equation basically would turn this into a 1, so we would have K1 minus N1 minus N2 over K2. So as the population size of our second species, which is N2, as that increases, it makes this term get smaller and smaller. So as N2 increases, then our growth rate, because this term here is multiplying by the growth rate times the population size, so it's modifying that. So as N2 gets bigger, then dN dt gets smaller. If the competition coefficient is greater than 1, then we know that interspecific competition is greater than intraspecific competition. It's stronger. So you're getting more problems from another species than you are from your own species. So interspecific competition is stronger than intraspecific competition if the competition coefficient is greater than 1. The opposite of that is if the competition coefficient is less than 1, then interspecific competition is weaker. Remember, intraspecific competition had a coefficient here of 1. If this is less than 1, it's weaker than intraspecific competition. So if the coefficient is less than 1 right here, then interspecific competition is weaker than intraspecific competition. It's pretty straightforward, not that hard to understand. Now we can take this a step further and we can say, well, these two species can actually coexist with one another when they both have a stable population, and so that they're both growth rates are both 0. So when your growth rate is 0, so that means we're putting a 0 here, and we're putting a 0 there, and you can solve for the population size of the two species. And we can look through this algebraically with the equations, and we can also look through this graphically. And I find it much easier to look through the whole system graphically. Just to go back to the last slide for a second, just to recap the questions that we have. What happens to the growth of the population as the population size increases? So we know as the population size increases for both species, it has a negative effect on their population growth. That's the logistic model. And then what does it mean if competition coefficient is greater than 1? So we know the competition coefficient being greater than 1 means interspecific competition with another species is stronger than intraspecific competition with a co-specific member of your population. Excuse me. And if it's less than 1, it's the opposite. Intraspecific competition would be stronger than interspecific competition. And often it is. Often, because the members of your own species, we all want the same thing. We're all getting it the same way. So often intraspecific competition is very strong. So when will two species coexist? In general, Lotka Volterra predicts coexistence of two species when for both species, interspecific competition is weaker than intraspecific competition. If you're having more trouble with your own population than you are with another species, it's likely that you are keeping your own population in check, and you can coexist with the other species. When I said before, you would, if you had a population that's not growing, when the population is stable, the dn dt, the rate of growth is 0, and you rearrange the equation and you can figure out what the population size is for the two species. And so we can see the population size of species 1 equals its carrying capacity minus the coefficient of competition with the second species times the second species population size. And the same thing is going on with the second species. So effectively, we're really looking at, we can graph these as lines. And these are lines in the graph where the species is not growing. So the population is stable, the dn dt is equal to 0 at these 0 growth isoclines. So the rate of population growth is going to be 0 on these lines. And when we're going to do this graphically, if we're above the line, the population will have a negative growth rate and has to move towards that line, decrease in size. And if you're below the line, if you're smaller than where the population is stable, then your population is going to grow until it reaches that line. And really, you're looking at that line is where the carrying capacity is being just impacted by the size of the second population. This is much easier to show you graphically. We're going to start looking in a graph of what is called species space. In species space, the x and y axes are just the population sizes of our two species. So here, my y-axis, I'm going to put species number 2, and across here on my x-axis, I'm going to put species number 1. So it's going from 0 to high, whatever high number is, and 0 to high, so you know what direction your axes are going. And you could be in anywhere in this space. So I could have lots of species number 1 and lots of species number 2, or I could have a little of each, or I could have lots of species 2 and very little of species 1. So I could be anywhere in this species space. But we know that there's certain places in this space where the population is going to be stable, because we had figured out if dn dt was 0, the population, if it's 0, the population is not growing or shrinking. And when we rearrange those equations, then we found that for population of species number 1, that occurs at carrying capacity minus the competition with species 2. And for species 2, that occurs at its carrying capacity minus competition from species 1, which is alpha 2, 1 times n2. So what you're really finding is that the population size of species 2 is dependent on the population size of species 1 and vice versa. So let me just take this isocline then, where things are stable, and graph it for species 2. So I'm going to use a red line for species 2. I'm just going to make up a scenario here. Species 2's maximum population would be its carrying capacity, and then it crosses the x-axis where that has just been modified by the coefficient with species 1, so alpha 2, 1. And so if it happens I have more species, more individuals of species 2 that falls above the line, that means the population would have to decline. And so for species 2's population decline, because it is on the y-axis, it would have to be going in that direction until it hits the line, and then it stops because that's where it has a stable population. If I happen to have very few of species 2, its population is going to be going up until it hits the line. All right, let me put on the line for species 1. I'm just going to make it a line here, and I'm going to make its line in blue just to be consistent. And let's just say you're colorblind and you can't see these lines clearly, or these colors clearly. You can tell from the intercepts which line is which. So this is going to be the carrying capacity of species 1. And over here, it's going to be the carrying capacity of species 1 divided by the competition coefficient of the impact of species 2 on it. So now, in order to see how these models work, in your textbooks, they put some confusing arrows. I'm going to explain how to do this in a very simple, easy way, and you're going to appreciate it. So let's start. Let's just say I went out there and I measured how many of species 1 and 2 I have in a particular location. So I have this many species 1, if I look down here, and I have that many of species 2 if I look over there. So I know that I am above both of those lines. Now, to figure out what's going to happen to my population size, what I'm going to do is I'm going to do it one species at a time. So let me start with species 1. Species 1's on the x-axis. So if species 1's above its line and its population is going to decline, it has to move only left or right. It's x-axis. So it's going to be moving to the left because it's in decline, it's above the line, until it hits its line. So we can just take species 1 and we can have it drop until it hits the line, and now it's stable. But now we're above the species 2 line here. So now species 2, when it declines, it's on the y-axis, so it has to go down to decline. So it's going to go down until it reaches its line. So that's species 2. Now, in a lot of books, they will show you these combined trajectories going across here, going across the lines here, and it just doesn't make sense until you see the two trajectories separately as to what's going on. All right, so now we're below species 1's line, So species 1 has to increase its population back up to its line. We're above species 2's line, so the population is going to decline. And oh my goodness, it not only declined, it crashed. So species 2 has completely disappeared. Now species 1 is free to increase to its line till it gets to the carrying capacity. So species 1 won. Let's try another example. Let's try somewhere else. So let's say we start over here. So we start over here, and it doesn't matter which species you start with, but I'm going to start with species 1. And so it's below its line, so it's going to have to increase to get to its line. Then species 2 is above its line, so it's going to decrease, and you're going to end up back at the carrying capacity again. It doesn't matter where you start. I could start in the middle here, and I could go up to species 1's line, down to species 2, species 1, species 2. Doesn't matter. In this particular scenario, where the line for the species 1 is above the line for species 2, species 1 is the winner. Species 1 wins the competition every time in this species space. I would replay this if I were you. Go over, see how this works, draw some graphs, practice it on your own, and it'll be much clearer than the little arrows they show you in your book. So this is the way it's showing in the textbook we're using. This diagram is particularly annoying because you can't even see the different colors on the lines here. But I know from looking at these intercepts that I know this bottom line is species 2 and this top line is species 1. So that's exactly what I had before on the previous slide. So we have species 1 is on the x-axis, species 2 is on the y-axis. So the species 2 line went from here to here. We can mark the intercepts. Put that in the right color. Species 1 line is the wrong color. And so it's got its little intercept down here. And these are the arrows that I was talking about. So this first arrow doesn't seem to make a lot of sense. None of these arrows seem to make any sense. So let's just say I'm going to start with where this arrow started. I can start here on my graph, and so take it one species at a time. I'm above species 1 line, so species 1 is on the x-axis this way, so it has to go down to its line. So I'm on the species 1 line, I'm going to go this way. Now I'm above the species 2 line, so it's going to go down to its line, then it's stable. Then once again, I'm below the species 1 line, so species 1, it's going to go up to its line. I'm above 2's, and I end up in the middle. It does, at the carrying capacity. It does not matter where I start. It's going to work anywhere. So let's say I started with the one that's the arrow that starts in the middle here, and I'll use a different color. I can start here. So I'm below the species 1 line, so I have to go up. So to go up to the species 1 line, I go to the right. I'm above the species 2 line, so I have to drop down to it. I'm below the species 1 line, so I have to go to the right again. Above species 2, we're going to drop. Marker, and then I'm below species 1, so it's going to go back up. So in this case, you're always going to end up at the carrying capacity of species 1. When you study these Lotka Volterra competition models, they will show you these 4 different scenarios. And so all of these are using the same species space. It's just how the lines have been placed in that species space. And so once again, looking at any of these, do not use these confusing arrows that they show you on these graphs. Instead, do it one species at a time. Alternate species 1, species 2, species 1, species 2, or it doesn't matter which one you start with. As long as you're alternating between species, you will end up in the right places. I'm going to run through each example, not to annoy you, it's just to give you practice. You should be drawing these yourself. You can always skip ahead if you kind of got it already. So here I'm looking at, on the x-axis, species 1, on the y-axis, species 2. Here, in this case, I can tell that the species 2 line is above the species 1 line. So at a glance, you probably know what's going to happen. But just to make sure that you do, I'm going to draw my species 1 line here, which is going from its carrying capacity to its carrying capacity divided by the impact of species 2 on it. Then I'm going to do my species 2 line. Seems to happen to me every time. Species 2 line here, which is going to go from its carrying capacity to it affected by species 1. And then it doesn't matter where I start. So let me start with that one again. I can start right here. Do this in green. Start right there. I am above the species 2 line. Remember, species 2 goes up and down. So now I'm going to drop down to my line. I'm above the species 1 line. I have too many of species 1. Species 1, remember, goes left and right. I'm above its line. I got to go left. So you're always being attracted to the line. Now we're down there. Now I'm below the species 2 line. So species 2 has to increase. So I'm going to go up. I'm above the species 1 line. So species 1 will have to go to the left to decline, and it runs out of line. So it's going to hit 0. And then species 2, we're below its line, it goes up to its carrying capacity. So species 2 wins. Doesn't matter where I start on this one. You should work through a scenario where you're going to start in this middle region, down in this left, up in the top. Start anywhere. You should be ending up with species number 2 winning. Now remember, these isoclines are where the 2 species populations are stable. So in this example, it's nice they shoved it all into the bottom corner of the graph, but in this example, we can see these lines cross. And if I look at the intercepts for these lines, I have the species 1 line is going this way, and the species 2 line is going that way. And they cross at this spot in the middle. So where they cross, those 2 isoclines are equal, which means the population size of species 1 is at the point where it's not going to be going up or down. And the population size of species 2 is not going to be going up and down. So we know at that point there is some sort of equilibrium where they coexist. However, if you look at this, we see arrows going off in all different directions. What the heck's going on? So maybe we should figure out what is going on. So let's graph this guy out. So we've got the population of species 1, population of species 2. We have the isocline for species 2 here. We've got the one for species 1 there. I've kind of just spread them out a little bit more. So species 1 is going from K1 to K1 divided by the competition coefficient, which is alpha 1, 2, and then species 2 is K2, it's a K, sorry for my messy handwriting, K2 divided by the alpha 2, 1. So let's just say we're somewhere in, we'll start here, in that area. So I'm above species 1 line. So species 1's population has to decline. I'm below species 2 line, so its population's going to go up. Species 1's going to decline, and species 2 wins. Okay, so let's try somewhere else. Let me look. Let me start down there, bottom left. Species 1 going up to its line. Species 2 going to go down to 0, and then species 1 wins. Well, that's weird. What if I start right where the lines cross? Neither of them change. So, right where they coexist, that's at equilibrium. However, let's just say a storm comes through and the amount of species 1, some of the species 1 get wiped out. So they were coexisting, it was just in a perfect balance, and then we find out that there's a storm comes through, and so instead of being there, we're right here. Now it could be we're below species 1 line, it could go right back and they'd be fine. But I say you could start with any line. Let's say species 1 doesn't recover as fast as species 2. So let's say species 2 gets a jump on species 1. It's below its line, so it's going to go up. And once it's going up, then we're above species 1's line. It's going to go down, and species 2 is going to win. So little slight differences are going to determine who's going to win this one. You have what is called an unstable equilibrium. Sometimes species 1 wins, sometimes species 2 wins. If you do happen to hit that sweet spot and then something knocks you off the sweet spot, the chances are you're not going to get back there. One or the other is going to have an advantage and win it. So this is a pretty cool one because you really don't know who's going to win. And this is a pretty interesting situation that where the lines cross, but you don't have a clear idea as to who's going to win this one. This one, I can tell you, the punchline on this one is going to be the only one that gives you a stable equilibrium. And so we know we have an equilibrium because we have the two lines crossing. And look at all those red lines pointing in. So let's see what's going on here. We know that this is the species 1 line with ending up in the species 1 carrying capacity. So this is the species 2 line. In the previous example, those were reversed. So species 2 was sitting up higher than species 1. And what it's basically saying by where the relative lines are is basically that's going to be determined by where these intercepts fall. And remember, these intercepts are going to be impacted by how much that coefficient is impacting the carrying capacity. So if this coefficient is small, this species has a very small effect. Species 1 has a very small effect on species 2. if the coefficient is small, that means it's not going to have a huge effect. It's going to make, it's going to be less than 1, and it's going to push this intercept out this direction. And the same thing happens if species 2 doesn't have a huge effect on species 1, it's going to push that one up. So where these lines fall is going to be affected by the size of those coefficients. And in this case, you're going to find for the stable equilibrium, the coefficients are going to be less than 1. Which means interspecific competition is less than intraspecific competition. So let's just work this one out again. We got species 1, species 2. I should be getting better at this. Species 2. Actually, I'm going to draw the lines a little closer to the way, showing that it's kind of moving out there. Species 2 is going from its carrying capacity to its carrying capacity divided by a very small competition coefficient. And then species 1 is going to do this. It's pushed it way up because it's got its carrying capacity divided by its competition coefficient. So that's got to be a big number versus its carrying capacity here. So let's start somewhere. Let's start where we have a moderate number of each species. So if we see we're above the species 1 line, we're going to move over to that. So we'll do going down to the species 1 line. We're above the species 2 line, so we're going to go down to that. We are now below the species 1 line, so we're going to go up to that. We're above the species 2 line. We're going to go down. We're below the species 1 line, so we're going to go over. And eventually, we end up on the sweet spot where we're on both lines, and we don't go anywhere. Well, let's just say a storm comes and wipes out some of species 1. We gave that example last time, so let's say we start out here. So now the species 1 responds quickly, and we go back to equilibrium. Well, we saw that before. But what if we decided that species 2 gets a jump on species 1? So species 2 is below its line. It goes up here to its line. Then species 1 and species 2. It goes back to the equilibrium. It does not matter where I start in this space. I'm going to end up, maybe I have lots of species 1 and not so many species 2. Let's see, I just go here and then there. Doesn't matter where I start. I end up going into the equilibrium point. So I end up, this is the only example where we have a stable equilibrium between these two species. And that is when interspecific competition is not as strong as intraspecific competition. So work through these 4 graphs. Make sure you could draw them from memory. You should be able to do this. And you should be able to predict from anywhere that you start what species is going to win and be able to show that. And I think it's a lot easier to do it if you take it one species at a time than if you use these trajectories that they show you with the red arrows. So now you know how to do it, and you know it as well as these guys. So I have here on the left, we have who do we have? We have Volterra on the left, and we have Lotka on the right. Lotka was born in the Ukraine, moved to the U.S., and Volterra was Italian. They were both sort of mathematicians interested in biology. Volterra was interested in trying to come up with a way of looking at marine fish communities that was the overfishing problems that were happening with that. And Lotka was also looking at species competition. So they worked on these things independently, and so they were since they were both publishing it around the same time, and the work was done independently simultaneously. We credit both of them when we talk about these equations. Um, Now, the work that Gauss did, Gauss was actually taking this and extending it into a lab experiment. So he wanted to predict to see if these models worked. And he was using Paramecium single-celled organisms because you can get their population sizes growing quickly. You can do what you want with them. No animal rights people are going to bother you. And so they're very easy to use. And we've already talked about Gauss because he talked about what is called the competitive exclusion principle. He was interested in the importance of competition and really in understanding evolution and the idea as to whether you could competitively exclude one species by the other species if they were too similar. And we talked about this when we were talking about the niche. So he did these Paramecium Lab Experiments, two different species of Paramecium, Paramecium caudatum and Paramecium aurelia. They feed on bacteria. And he was, first of all, he had to figure out how strong was intra-specific competition, which would be the impact of the competition for food, for eating the bacteria. So he grew them with half strength of bacteria and full strength of bacteria to see how these two species. Now, this is a terrible graph. Let me just say straight out that I don't understand. You know it's a terrible graph when you look at this x-axis, and it's really not clear why we're going from this. This is the biomass of bacteria, or biomass of Paramecium, but I don't understand. You've really got one graph parked on top of another graph, and you put the full strength one below the half strength. I don't like it. Let's take a look at it a different way. Here we go. I'm feeling a little bit better now. Now I actually have the two graphs here. You should be able to explain these now. So the green dots are showing you the Paramecium caudatum, and let's look at them with the lots of bacteria available. So its lines going up, and then it's settling off at a carrying capacity of 137. And then over here, it's leveling off at a carrying capacity of 64 when you had less bacteria. So this is, as you reduce food, you increase competition for food, the amount of intra-specific competition increases, so it decreases the carrying capacity. And we have this exactly the same thing happening when we're dealing with the line with the Aurelia. Look at this, we've got exponential growth, and then logistic growth levels off, and we got the same thing. So actually at the beginning, it looks like the caudatum's doing better, but then the Aurelia actually does better in the long run at its carrying capacity. I found this short clip from a video showing Paramecium eating bacteria through the microscope. You can see the groove here. You can see the little cilia working away, scooping in the bacteria. And then it's going to scoop it into making a little vacuole. Got vacuole forming here. There's the oral groove and the vacuole. And then the vacuole is detached, there you go, with all the food, and it can digest that away. Another vacuole is forming, filling up with food. So back to the experiments he was doing. The resource limitation was seen with the different concentrations of bacteria. When grown alone, the carrying capacity was determined by intraspecific competition, and then he grew them together. And when he grew them together, he saw that Paramecium aurelia survived and Paramecium caudatum quickly declined, and assumed that the resource supplies were reduced by increased competition from the other species, and interspecific competition caused the local extinction of the Paramecium caudatum. So here's this favorite thing of putting two graphs together, one on top of another. The bottom graph is the caudatum, and the top graph is the aurelia. We have the days of the experiment across the x-axis, and the volume, the biomass of the organisms on the y-axis. And so we can see separately are the blue lines where you can see the carrying capacity of aurelia, and we can see the blue line for the carrying capacity of caudatum. But when you put them together, the aurelia certainly survived, but at a lower carrying capacity, probably because of the interspecific competition. Remember, competition hurts both species. And then the caudatum seemed to be initially doing better, but then as the aurelia population was increasing and eating the bacteria, the caudatum population declines and eventually disappears. This is the data from actually Gauss's paper. Aren't you glad we don't have to draw our graphs by hand? So it's exactly the same, but a couple of things I wanted to point on this. One on the two species graphs where they're grown separately, he actually has the logistic growth curves listed here. So the logistic growth curves include the growth rate for that population times its population size, and then its carrying capacity minus its population size. And then he also has the Lotka Volterra equations listed on here, which you can see have exactly the same population sizes, or sorry, the same growth rates and the same carrying capacities, but it's added in this other term. Instead of using alpha 2, 1, he used beta. Sometimes you see that for the second species, they'll put beta, they're alpha and beta, and those are the competition coefficients. I like using the alpha 2, 1 and the alpha 1, 2 because it's very clear on who's competing with who. And then it has the population size of the other species listed there as well. This last example I'm going to look at is Tribolium flower beetles. Flower beetles have infested our milled grain for 4,500 years. So they've been around for a while, and they've been studied a long time because obviously we want to figure out how to control these guys from eating our grain. And there's two different species we're dealing with. We're dealing with Tribolium confusum and Tribolium castaneum. And this was work done by Thomas Park in the 50s. And he was looking at the different conditions. So first of all, he grew these guys individually by themselves. And you can see the top graph is just showing you that when he grew them by themselves, that they level off. This is obviously dealing with logistic growth, but you can still see there's still ups and downs. There's still things going on with logistic growth. The logistic growth equation does have some interesting behavior, especially at relatively high growth rates. But then when he grew them together, sometimes one of them won, sometimes the other one won. Remember, we had that graph where we had sometimes species 1 winning, sometimes species 2 winning, and it seems like that's what's happening here. Really, it wasn't terribly predictable. The species that sort of got going faster won out in the competition. This is called the priority effect, and we actually see this quite a bit in nature, that we can't really predict who's going to win because we're not sure who's going to get the jump. It could just be something quite subtle change somewhere. It could be genetics. It could be, that particular population. It could be the humidity is just right for them, or something that causes them to get the jump on the other one. So really we can see that obviously two species growing together is going to affect each other, and that means competition is affecting a lot of species living in the natural world. The next section of the chapter, we're going to talk about competition and then how that it does affect the niches of different species. And we have quite a few experiments and examples on how the competition between species is impacting their niche. So join us for that one, and we will see you soon. Kangaroo Rat's sitting here watching you.